It's a great pleasure to have the opportunity to share some of the stories we have been investigating over the years. My group works in various aspects of open quantum system, non-Markovian, temporally correlated noise. I had a hard time picking a topic, but I decided to go with this story because perhaps this could be an audience that can help us making headway towards looking for these particles, or quasi-particles, I should say, and like Amir emphasized in his lecture yesterday, make sure that certain things don't exist only in the very active imagination of theorists like me. So I am pretty sure that I either will go over time, or in any case, I won't be able to explain all what went into this work. So let me give you main references. These are these two papers, and the good thing is, if you have additional or will have additional questions, Vincent, the lead author of this paper, is here with me. We will also have a poster together with this. Let me also acknowledge my longtime collaborator, former postdoc Emilio Cobanera. Some of you might know him. And even though I will not directly talk about this work, this is also related to the main theme. And this has been done with another graduate student of mine, Mariam. So what is the broad context this story touches upon? More or less directly, Amir touched upon topology. I will be the one touching on it most explicitly so far. So the big challenge here is to try understanding what are the role, the implications that topology has in classifying, characterizing phases of light and matter could very well be like spin for this audience, and particularly with not only naturally occurring phases of matter, but phases that we can engineer with control capabilities at the many-body level, maybe far away from equilibrium condition. I don't think I have to spend much time to justify this pointer is really funny. There is a lot of retardation effects. I don't think I have to justify much why this is both fundamentally and practically important. I would say it's gaining a lot of traction also from the point of view of harnessing topological effects toward making interesting new devices on top, of course, of the main theory challenge, which has been and remains finding an organizing principle beyond Landau to talking about phases. So let me just call attention, because this is going to be the prerequisite for what I'm going to be talking about, a stepping stone into building an understanding of topological phases of matter as being understanding what are regarded as the simplest one in some sense from a condensed matter point of view. So symmetry protected topological phases, SPT for short. And I will interpret them, this is kind of important for what comes after, as being phases of fermionic matter, which are fully gapped at the many-body level, and importantly, they are phases of free fermions, or non-interacting, by which we mean, in the majority of cases, that the interactions are there, but they are accounted for at a mean field level. Now, I think, as many of you know, over the years, we have succeeded getting a very pretty complete understanding of the topological properties of these phases, and there has been like a famous tenfold weight for classifying them based on symmetries and determining the type of topology, and in particular boundary states that these phases support. I mentioned bulk, I mentioned boundary, and one of the most remarkable consequences or cornerstones of this type of physics is the so-called bulk boundary correspondence, which entails a relationship between certain bulk, topological invariant, and the emergence of topologically protected zero modes which are localized at the boundary of the system. And because I will aim to talk about Majorana bosons at some point, let me call attention on some of the paradigmatic topological phases. SPT phases is topological superconductivity, in which case think about like Kitaev fermionic chain as being the paradigmatic, simplest case in one spatial dimension, the type of bulk boundary and the type of states, edge states that I alluded to. In that case, they would be associated to zero modes or like which are associated in turn to Majorana, fermionic quasi-particles, and I have listed here properties that, sorry for being pedantic, but it's worth keeping in mind because we will aim to generalize them. I have already said these are zero modes. They are exponentially localized on opposite ends of a chain if we are thinking 1D, which is the simplest setting. They are described in second quantization by a pair of Hermitian operators that will be almost conserved quantities. They will commute in the thermodynamic limit with the Hamiltonian. They have like a certain algebraic structure to them. This is encoded in the Majorana algebra, and physically, aside from the anti-commutation properties, the idea is that if we have these two Majorana entities, we can combine them, they're canonically conjugated, and we can combine them, we can view them as real or an imaginary part of a spatially localized split fermionic Dirac degree of freedom. I mentioned zero energy. Zero energy, why is that important? Because these fermionic states can be empty occupied, and being at zero energy, they can therefore mandate ground state degeneracy, and this happens. This is at the many body level. So the many body ground state is twofold, degenerate when we have this quasi-particle in place. So the question we set ourselves up to exploring a few years back by now, it's taken some time, is can we have anything similar to SPT phases of matter, just like I have described for free fermion, but let's just change fermion into boson and keep the freeness, keep as much of the ingredient common to the story as possible. Well, as many elements equal to fermions as possible means, let's start from Hamiltonians, which describe a system of non-interacting boson. So if we take it to be in equilibrium, we are going to have like a Hamiltonian, which is quadratic in certain bosonic canonical creation and annihilation operators. And if we go with the analogy with fermions, Hamiltonian, we are going to take them to be, of course, many-body Hermitian, and also we want them to be bounded. Bounded from below or bounded from above is going to be the same, but let's say bounded from below. Well, it turns out that if we keep all of these constraints in place, there are provable no-go theorems that we formalized a few years back that says that no symmetry-protected topological phases are possible at this level of free bosonic Hamiltonian equilibrium systems, and likewise no zero modes are, can be possibly emerged by this. Essentially what happens is that any type of Hamiltonian that might come with certain symmetry can be adiabatically continuously deformed into another that shares the same group of symmetries, and this can happen without at any point these symmetries being broken or the many-body gap being closed. So there is something fundamentally different between free fermions and free boson, and in order to make headway, we need to change some of the ingredients in the picture. So notice that I don't want to say that it's not possible to have interesting manifestation of topology in free boson if we relax some of these constraints. So for instance, if I decide that I'm interested not specifically in zero energy protected modes, but I allow for higher energies, then yes, we can have very interesting structure, which come with some topological protection. I stole this picture from this paper here, and this is a two-dimensional Kagome lattice theoretically realized that supports topologically insulating magnonic states. But also, I could insist instead in zero energy and let go of the Hamiltonians being bounded from below. This is something that also can give rise to some kind of like localized edge modes, but it's also possible to prove that with that, they come and they are extremely fragile against perturbation because the system sits at the boundary of dynamical instabilities. So why not do something a little bit more audacious and leave Hamiltonians all the way behind, at least Hermitian Hamiltonians, and go towards the world of open quantum system and repurpose the search for non-trivial topology there. So in that case, as we have heard, thankfully, speakers before me did a wonderful job in talking about essentially open dynamics being describable very often at the semi-classical or phenomenological level in terms of a non-Hermitian effective Hamiltonians, or at the fully quantum level, at least for the large class of system which we can take to obey Markovian dynamics via Lindblad equation. The two descriptions can be related. Often, if we are able to neglect the quantum jump terms, we can have an effective non-Hermitian Hamiltonian directly from a Lindblad equation. All to say there are various descriptions which are possible. Each of them has led over the past year. These are just some of by now old, because this has been a very rapidly evolving field, but some references showing that there are indeed very interesting physical phenomena, like very good possibilities for sensing, or novel modalities for lasing modes, or like novel types of phase transition which happen in steady state. These come up all also for bosons, but in open system setting. That being said, we were taking the lenses of some, like I said, we were coming in from like many-body condensed matter point of view, and if you look at all of the phenomena, well, I cited very few of them, but the many more that are there, you look back at what the SPT fermionic physics is, and it seems like these two worlds still have very little in common. So the question we wanted to push is, can we really do better? Can tighter bosonic analog of SPT phases exist, or is this as far as we can go? Well, I wouldn't be here giving a talk if maybe the answer would be a resounding no, but let's see how to get there. So in this case, the type of like setting that we have considered is, in a way, the simplest type of Markovian dynamics, which still can physically describe non-interacting, in field interacting. So it's also in information, in continuous variable quantum information is called Gaussian Markovian dynamics. And it is described in the Heisenberg picture. If this represents an observable, we can have a Lindblad equation written directly for observable. The Hamiltonian, as before, will be quadratic in the bosonic degrees of freedom. And in order for the full generator to also be quadratic, this will constrain the allowable Lindblad operators to be at most linear in the bosonic creation and annihilation themselves. There are some notational settings that we have to have, but let me just emphasize that if we look at the equation of motion for arbitrary linear observables, they can be obtained. They have a very compact form, and they can be described in terms of a dynamical matrix from a system theory point of view, what we end up getting is a linear in the state variable A and A dagger variable, a linear time invariant system where the generator of these dynamics is this matrix, which is related to the Hamiltonian contribution, except there is a little matrix, tau 3. Think of it as an ampliated sigma z matrix, where n is the number of the lattice sites that I am considering. And the most important takeaway message that you have to have at this point is that this matrix here need not be normal, need not be Hermitian, even though I should stress that I am not working with an effective Hamiltonian here. The many-body Hamiltonian I have is perfectly Hermitian, and this is a Lindblad, a complete Lindblad master equation. I'm not throwing away any term. So perhaps I should add some insight. The reason why this non-normality emerges is purely due to the bosonic statistics that our degrees of freedom obey. Now, because we have bosonic degrees of freedom, the interesting feature that comes in the dynamics due to this effect, due to the fact that also the state space of even a single bosonic degrees of freedom is infinite dimensional, the dynamical stability properties of these linear time invariant systems can be more interesting and richer than we would have just for a fermionic counterpart. So let me remind you that we call a system to be dynamically stable if for every possible initial condition and every observable of interest for the system, we want expectation values to remain bounded. Benedetta, is that a question?
Yeah.
Yeah, please, sorry.
No,
yeah.
So when you say that this non-normality comes from
yes.
being bosonic,
yeah.
so then the non-normality is there even if you don't have the Lindbladian part? I mean, is it something associated with the Hamiltonian
yes.
pseudo-Hermitian because it's like a Bogoliubov?
Excellent question. If you consider the limit of a purely closed system, you are perfectly correct in saying that the statistics, the bosonic statistics can induce an effective non-hermiticity, and I'm looking at Ash because, in fact, in a paper which is cited later, he was pointing out this fact, which is well known also from Blazoricka, from many-body physics, but he was given an incarnation of how essentially phenomena which are usually tied to, like skin effect, to properly non-Hermitian system, they can be engendered due to the fact that we can have, in the presence of number non-conserving terms, even at the Hamiltonian system.
But if you don't have the Lindbladian part, it should still be pseudo-Hermitian,
yes,
right?
very correct. In the purely Hamiltonian case, or whenever we can have this term being 0, which doesn't happen only in the Hamiltonian case, you are absolutely correct. We have a pseudo-Hermitian effective system. So physically, I said it very quickly, but let me remark that actually the factor of breaking or retaining number symmetry, U1 symmetry, is key in order for this type of non-normality to emerge or not. So, okay, we were talking about dynamical stability of the system, and that being the requirement. How to diagnose the dynamical stability of the system? It can be done by looking at a spectrum. Conventionally, we put an I, a minus I factor, and the eigenvalue of that form what we call the rapidity spectrum. Don't ask me where the name came from. I would be curious to know why they're called like that, but I don't know. It's very important to consider, like, I would say, two types of gap. We have the spectral gap, which is the usual quantity that determines the asymptotic approach to steady state also in the finite dimensional system for a semi-group for a Lindbladian. But also let's pay attention to what we call the stability gap of the system, which is instead defined by this other relationship. And in this case, like I tried to summarize, basically all the possibilities are allowed here, depending on whether the stability gap is negative, strictly, or positive, or 0, which is kind of like a marginally stable state. So the case where the stability gap is strictly 0 is the case where the semi-group is dynamically stable. We have a unique steady state. And in fact, in that case, it's possible to show that this stability gap is actually equal and opposite to the spectral gap itself. In the opposite case, where we have a stability gap which is strictly larger than 0, oh my goodness, I knew it. We have a dynamically unstable system, no steady states, and don't ask me about the intermediate case because that's the one which is most undecided. Okay, so moving on very quickly, we zoomed into, but I had some questions, so take 2 minutes. We can move to a subclass of these one-dimensional QBLs, quadratic bosonic Lindbladian, and assume that we have no disorder in the bulk. So we have translational invariance up to boundary condition at the most. So we can have like finite system with open boundary condition, by infinite, which is very similar to having things on a ring, if you want, periodic, or semi-infinite, which is the case where we really have still boundaries, but the size of the system goes to infinity. Now, the key message which I would like to release here is the fact that if the dynamical matrix of the system is non-normal, possibly highly non-normal, there are very non-trivial behavior that can occur when we consider a sequence of spectra of finite size systems under open boundary conditions and the limit where the size of the system becomes infinite. So in general, this equality is violated, and it is possible for the limiting spectra of the finite size to actually not be coincident with what one would think the thermodynamic limit to be. So in my mind, loosely speaking, I think of this as breaking of a finite size scaling type of assumption. So this opens the door for a class of systems that we call dynamically metastable, because it is possible, and this very quickly is a cartoon picture of where in the complex plane the rapidities can be located. It is possible to be dynamic. It can be dynamically stable for arbitrary finite system size, and yet unstable in the infinite size limit. Why is that important? This is important. Well, as you can see here, I also noted that the mathematical tool for capturing this discontinuity is not really spectra, but is something a bit more sophisticated and more robust to changes, which is the pseudospectrum. But let me go to actually the goal of the talk. And the goal of the talk was the search of non-trivial bosonic SPT phases. So to summarize here, what we want to get is to uncover in 1D for now, bulk translational invariant QBLs, and we want them to have two properties. Well, we want to require dynamical stability, so finite spectral gap, because we want to have a well-behaved system with a unique steady state. But at the same time, we want to see whether it is possible for the system to host modes which are edge localized. They are protected in a topological sense, and so they come with a topological invariance. Now, almost there, but there are two complications that we have to face with this, because on the one hand, I am saying that we need a zero mode, which means a zero rapidity in the setting I have described, but this in itself will mandate a closing of the spectral gap. So how can we put these together with the requirement of stability? The solution is exactly the pseudospectrum, which I mentioned and I couldn't explain very well. But in a nutshell, if the system is not normal, it is possible for the QBL to have a non-zero spectral gap, so to retain stability, and nevertheless an approximate zero rapidity, And so it falls into the dynamically metastable class that I was describing before. So this metastability in the dynamical sense opened the door for searching for what we want. The second caveat is that I said about fermionic Majorana modes that they are conserved quantities, they're zero mode. In a Hamiltonian case, this really doesn't make a difference. As soon as we have some operator in second quantization that commutes with the Hamiltonian, it can be a zero mode, it's conserved. And also, if you put it in an exponential, it can generate a continuous group of symmetry. Not so in open quantum system because the correspondence between symmetry generators and conserved quantity breaks, which means that in searching, at least I can introduce you to the Majorana bosons. In searching for analog of Majorana fermions, we have to be open to the possibility that they are either zero modes or conserved quantities. There is no a priori reason for searching for one or the other. Let's allow them for both. And in essence, here I have summarized the properties that these dynamically metastable QBLs have when they support Majorana bosons, with one thing I haven't said yet. Dynamical metastability in itself, 0 minute, thank you, is not enough. What we also want is a topological invariant, and the topological invariant is a certain winding number about the zero in the complex plane, which is zero rapidity, which is the analog of having the zero energy in the Hamiltonian case. So the upshot, there are properties, there are canonically conjugated edge localized modes that we can predict in appropriate conditions, and the key difference, or one key difference with respect to Majorana fermions is that they are not tied to ground state, they are not tied to steady state, they exist in the metastable transient regime. And with that, I would like to tell you what to expect. Wow, well, I'm sorry, my slide doesn't show properly. What to expect, for instance, in Vincent's poster, where to find them, how to engineer. It is possible to find a variety of settings on paper. The question is how to realize them in systems where either in purely dissipative setting, or here comes the system I was alluding to, where Alex McDonald and Ash, this is the bosonic E-type chain, you can interplay with dissipation and have Lindbladians, which provably exhibit these modes. Lastly, do they exist in our mind, or maybe is there some hope that they could be seen? In order for them to be seen, we need signatures. The signatures that we predicted could be, a smoking gun for these entities. They are related to two-time correlation functions and power spectra. And there are various of them that we can put up, for instance. But the upshot is that if these things are to be observed, we expect that they have long-lived correlation despite macroscopic separation and being the counterpart of a split, fermion. We have a split boson here. It could be a split magnon, it could be a split photon. This is up to the incarnation that we are going to find. These are my conclusions, and I apologize for the overtime, but I know we have a break. So the upshot, and please ask me more questions, please come by to the poster because this was impossible to absorb. What I would like you to take away is that we might have, for bosons, to take a departure away from many-body ground states and even away from many-body steady state. There can be interesting topological physics in appropriate transient timescales whose duration is long. And long means extensive, growing with system size. So this is what I have alluded to with topological metastability, and we think we have found a pretty tight, or as tight as it can possibly be, analog to Majorana fermions In the case of bosonic systems, we also have analog of Majorana or Dirac bosons, which are the ones for number-conserving QBLs. Lots of questions. First and foremost, do they exist? Can we see them? But then a lot more that I would leave for discussion. Thank you.